Hi everybody, this is lecture 5 about momentum. Let's go ahead and get started. So what is momentum? So momentum is a property of moving things, and it's in some sense a measure of inertia in motion. And it's not equivalent to inertia, but it's related. Its units are kilograms times meters per second. And in equation form, it's momentum equals mass times velocity, or P equals mv. So that's momentum equals mass times velocity. So it's mass and velocity together that gives you momentum. Okay. So momentum is mass times velocity. Changing either mass or velocity changes momentum. So you could change the mass of an object, or you could change the velocity of an object. Both of those things change the momentum of an object. And I think the word momentum is intuitive to us, meaning if something has a high momentum, it's got a lot of motion. If something's got a small momentum, it's got a little bit of motion. And in combination of the size of the object and its velocity, those together determine momentum. Okay, so something like doubling mass only doubles momentum, or doubling velocity only doubles momentum, or doubling mass and velocity at the same time quadruples momentum. And that comes from P equals mv. Okay, so a car of mass 2,000 kilograms moving at 40 meters per second has 4 times the momentum of a car of mass 1,000 kilograms moving at 20 meters per second, because they're both doubled. Twice the mass, twice the speed, 4 times the momentum. Okay, a moving object has momentum, that's true. Energy, that's true. Speed, that's true. So all of the above. Okay, when the speed of an object is doubled, its momentum remains unchanged in accord with conservation of momentum. That doesn't sound right. When the speed of an object doubles, the momentum doubles. That sounds right, because when speed doubles, momentum doubles. That sounds right. So let's go with B. Okay. All right, impulse. Impulse is a change in momentum. So if you have an object with some momentum, something from the outside comes in and affects it and changes the momentum. So impulse is a change in momentum. And here's our equation for it. Impulse is I is equal to change in momentum. This delta here, the Greek letter delta, means change, and P is momentum. So change in momentum is equal to, if the mass of an object stays the same throughout an impulse, then it's just the change in velocity, and that's equal to force times time. Okay, so if we take a force and we act on an object, the force times the time gives you how much the momentum of that object changed. Okay, there's some examples here. A brief force applied over a short time interval. Let me read that again. A brief force applied over a short time interval produces a smaller change in momentum than the same force applied over a long time interval. Okay, so if we push an object with the same force, the one that acts for a longer time gives you more impulse. If you push with the same force for twice the time, you impart twice the impulse and produce twice the change in momentum. Yeah, so if you take a force and you push it for something for 1 second versus you take a force and you push something for 2 seconds, it's going to be twice the impulse. And then the greater the impulse exerted on something, the greater the change in momentum. I think that makes sense. Since impulse is change in momentum, the higher the impulse, the higher the change in momentum. Okay, when the force that produces an impulse acts for twice as much time the impulse is, well, if it acts for twice as much time, then the impulse will be doubled. Okay. Okay, impulse changes momentum. Let's reiterating this again. So here's a few example cases. So increasing momentum. This is like a golf club hitting a golf ball. Increasing the time of contact results in greater change in momentum. Okay, so if the golf club is in contact with the golf ball for a longer time, golf ball gets more momentum. Okay, force can carry throughout the duration of contact. Okay, so this is like golf club hits golf ball, baseball bat hits baseball, something hits something else, and it goes shooting off. Case 2, this is another example. Decreasing momentum over a long time. Allowing longer time to reduce momentum requires small average force. So if you want to slow something down, say you're in your car, you want to slow it down and you lightly hit the brakes, it's going to take it a long time to slow down to 0. Whereas if you're moving in your car, slam on the brakes, high force, It's a short time to slow down to 0. Okay, that's case 3. If you slam on the brakes, increases the force, the time required to slow the car down to 0 is very short. Okay. Impulse changes momentum, reiterating that again. Here's another example, how airbags keep you safe in a car collision. So assume a car and you have mass m traveling with speed v, that same impulse during the collision, but time during impact. Let's read that again. Actually, so what if we don't have an airbag and our car gets into a collision, then our bodies will use the seatbelt to create our change in momentum, which is a very hard, solid thing. So the time that the force is required to slow us down is very short, so the force is very high. So that's what this is showing here on the PowerPoint slide. The small time means the force required is large. So the airbag tries to do the opposite. The airbag tries to increase the time it takes to slow you down when you get into an impact. So the time is big, so the force is small. When the force is small, there's less damage done to our bodies. So everything we do, airbags, seatbelts, crumple zones on cars, is to try to increase the time of impact so that the force required is less. And that's what this is showing. Higher time of impact, smaller force. If we don't have crumple zones, if we don't have our seatbelt on, if we don't have airbags, then the time of impact is very small, so the forces are very big, lots of damage done to us. Okay, so this is another example of how impulse helps explain what's going on. Okay, let's do some questions. A cannonball shot from a cannon with a long barrel will emerge with a greater speed because the cannonball receives a greater, well, I'm going to go with impulse. We're not sure about the forces. Cannons are complicated. I'm going to go with impulse. Okay. So we know we have this, if there's gas pushing the cannonball out, then it's going to be acting over a long period of time because it has a long barrel. So there'll be a large impulse. Okay, when compared to a short barrel. A fast-moving car hitting a haystack or hitting a cement wall produces vastly different results. Okay. Do both experience the same change in momentum? They do. But the car has a momentum at the beginning and it has 0 momentum at the end, whether it hits the haystack or the cement wall. Do they both experience the same impulse? Yes, they do, because they both have some momentum at the beginning and they both end at 0. Do they both experience the same force? They do not. With the haystack example, the time is really high, so the force is low. With the cement wall example, the time is low, so the force is high. So 1 and 2 are the same. So the question is, let's see. Do both experience the same change in momentum? Yes. Do both experience the same impulse? Yes. Do both experience the same force? No. So that's B. Okay. When a dish falls, will the change in momentum be less if it lands on a carpet than if it lands on a hard floor? So because a plate is starting and they both fall and they both end at 0 momentum, change in momentum is the same in both. Okay, so they're both the same because they both start with some momentum and end with 0. They are the same. Okay, bouncing. Impulses are generally greater when objects bounce. Okay, so if something, let's see an object here, I got my pencil. If a pencil drops to the floor and stays still, that has a specific momentum that goes from momentum going down to 0. That's an impulse. But if it bounces off the floor, then it's going down initially and it goes up after the bounce. And that's a larger impulse. Okay. Moving on from impulses here, let's talk about conservation of momentum. Conservation of momentum is the law, is in the absence of an external force, the momentum of a system remains unchanged. So as long as there's no interactions or forces coming from the outside world, the momentum of a system never changes. Okay, let's do some examples here. When a cannonball is fired, the force on the cannonball inside the cannon barrel is equal and opposite to the force of the cannonball on the cannon. So if our system is the cannon and the cannonball, momentum is unchanged in that system. The cannonball gains momentum while the cannon gains an equal amount of momentum in the opposite direction. The cannon recoils. So conservation of momentum explains why if you fire a gun or fire a cannon, there's recoil or kick in the opposite direction. Because while the bullet or the cannonball goes one way, the cannon or the gun goes the opposite direction. Okay, when no external force is present on a system, no external impulse is present, and no change in net momentum of the system is possible. Okay, so this is telling us that if we have a system, say a baseball, all the forces within the baseball force inside are all holding the baseball together. But because they're all internal, there's no external forces. The baseball has no change in momentum due to those internal forces. Same thing if you're in a car and you push on the dashboard. If you push on the dashboard, you and the car push on each other, and you can't push the car forward that way. So if there's no external impulse, no change in momentum. Okay. Newton's first law tells us that the motion of an object does not change when there are no unbalanced external forces. Okay. We can express the same statement in terms of momentum. Okay, let's do it. Momentum of the object is conserved when there are no unbalanced external forces, which means if an object is moving in a straight line with constant momentum, then there's no external impulses, then it will continue to move in a straight line with constant momentum. Okay, we can extend this to the idea of two or more objects. Let's do it. Total momentum of the system is conserved when there are no unbalanced external forces acting on a system. Okay, so if we're looking, there's objects, we have our system, it's got objects in it. If there's no forces coming from outside, just all the forces are internal, then total momentum will be canceled. And total momentum will be conserved in the system, meaning the total momentum won't change over time. Okay, so for example, I have this cup here. This cup has a bunch of internal forces going on inside the cup. Since for every force there's an equal and opposite force, all these internal forces cancel out, and the momentum of the cup isn't moving anywhere. It's only if I use my hand and throw it. That's an external force on the cup which changes the momentum. Okay, let's do some examples. Okay, conservation of momentum, applications to collisions. We'll get to some examples, we'll do some collisions. So the net momentum before is equal to the net momentum after. This is before and after collisions. Okay, an elastic collision occurs when it's a perfect bounce. Okay. An inelastic collision, when it's an imperfect bounce. Almost all collisions we deal with in the real world are inelastic collisions without a perfect bounce. Okay, so elastic, perfect bounce, kinetic energy is not lost. Perfect, inelastic, almost all of our collisions are like that. Not a perfect bounce, kinetic energy is not conserved. Okay, let's do some carts. Here we go. Okay, so freight car A is moving toward a identical freight car B that is, let me read that again. Freight car A is moving toward the identical freight car B that is at rest. So freight car B is at rest. When they collide, both freight cars couple together. Compared with the initial speed of freight car A, the speed of the coupled freight cars is, okay, so we have momentum initially. One freight car comes to a freight. Let's see if I can get something here. Get some gum. Okay, so we've got freight car 1 at rest, identical freight car. As they come together, they move, they stick together and move as one. The momentum before is m times v. The momentum after is m times 2v. So the speed of the couple cars must be half, because the momentum before is the same as the momentum after, but the mass doubled. It's got to be half. Okay, let's not, these are really complicated because Momentum is a vector, and a vector is an arrow with a direction. And so if we start getting into 2 dimensions and 3 dimensions, then we know we have to add up the vectors to see how momentum is conserved. I don't think we should get into this so much. Okay, this is another example. Okay, let's do some conservation of momentum examples. Let's do this example. So we've got a red ball here coming in at 6 meters per second, mass 4. A blue ball at -4 meters per second with 2 kilograms. The negative here means that it's moving to the left. The positive here means that it's moving to the right. Okay, so before the collision, let's add up their momentums, which is m1v1 minus m2v2, which is 24 kilograms meters per second for the red ball, minus 8 kilograms meters per second for the blue ball. So the total is 16, 24 minus 8. Okay, if they stick together at the end, after a collision, they come together, stick together, and they go off together. Then the total after is the mass times the speed. Okay, so we know before it's the same as the total after is the same as before, which is 16. And we know the mass total of the 2 balls that have stuck together is 4 plus 2, so that's 6. So then 16 divided by 6 is 2.67 meters per second. That gives us the final speed. So notice the p total before and the p total after are the same, even though the speed is totally different than the speeds of the initial balls. Okay, let's do some more. When a farmer throws a 3-kilogram pumpkin at a speed of 4 meters per second onto a compost pile, the pumpkin's momentum just before hitting the pile is, okay, momentum is m times v, so 3 times 4, which is 12 kilograms meters per second. Okay. Compared with the momentum of a 200-pound man running 10 miles an hour, the momentum of a 2,000-pound car moving 1 miles per hour is, let's find out, 200 times 10 is 2,000 pounds miles per hour. And the car is 2,000 pounds times 1 miles per hour. So that's 2,000 pounds miles per hour of momentum. So these momentums are equal, so they're the same. Okay, and this gives us some intuition. A small thing going fast can be equal to a big thing going slow. Okay, they're the same. All right, next one. A lunar vehicle is tested on Earth at a speed of 10 kilometers an hour. When it travels at the same speed on the moon, its momentum is, well, nothing changes the momentum. It's mv no matter where you are, in space, on the moon, on Mars, on Earth. So it's going to be the same because it's m times v. And the lunar vehicle's mass doesn't change whether it's on the moon or on Earth. And if it's moving at 10 kilometers per hour in both places, it's the same momentum. The same. When both the force and the time of contact are doubled, the impulse on an object is, well, we know impulse is force times time. If we double the force and double the time, that's quadruple the impulse. Okay, that was right. Your friend says that the impulse equals momentum. Your friend's statement is not correct, and the missing word is change. So impulse equals change in momentum. Okay. If a car comes to a full stop when hitting a haystack and when hitting a stone wall, the change in momentum is greater for hitting the change in momentum is the same in both cases, because when a car hits a wall, it comes to a stop. When a car hits a haystack, it comes to a stop. So assuming they started with the same momentum and the final momentum is always 0, then the change in momentum is the same for both. Okay. A 1 kilogram ball has the same speed as a 10 kilogram ball. Compared with the 1 kilogram ball, the 10 kilogram ball has, well, it's same speed, 10 times the mass. So that means 10 times the momentum. So 10 times as much momentum. Okay. Which of the following equations most directly illustrates the safety value of automobile airbags? F equals ma? Maybe. Ft equals delta momentum. That sounds pretty good. D equals 1/2 at squared. That looks like for how much distance you travel with gravity. And this looks like change in speed due to gravity. I think it's this one. Force times time equals change in momentum. Okay. A ball is tossed into a bale of hay. and comes to a stop. If instead it comes to a stop when hitting a sticky solid wall, the impulse needed to stop it is... Okay, so if we toss the same ball with the same speed and it hits a bale of hay, comes to a stop. Same ball with the same speed, hits a sticky wall, comes to a stop. In both cases, it started with some momentum and ended at 0. So the impulse is the same. Okay. So why do these feel different? They feel different because the bale of hay had a small force because it took a long time to exert the impulse. But the sticky wall was a solid impact. That was a short time, means a high force to create the same impulse. So the impulse was the same, but the difference is those times and forces. Okay, when a falling object bounces as it hits the ground, the impulse on it is greater than for stopping it. That sounds true. Its change in momentum is greater than for stopping. That sounds like the same thing stated twice, so I'm going to say both of these. Okay. When you jump from an elevated position to the ground below, the force you experience when landing does not depend on the jumping height. Sounds like more force if you jump from a higher elevation. The softness or hardness of the ground. Sounds like it does depend on that if you have a cushiony ground versus a solid ground. How much you bend your knees, it sounds like that matters because that changes the amount of time the impact takes. Your attitude about jumping. Okay, I don't think your attitude matters much. Well, maybe it'll change how much you bend your knees. So maybe it has, but physically, let's say the attitude. Okay, nets used to catch falling boulders on the side of rocky hillside roadways are more effective than rigid fences because their breakage is reduced by less impulse of falling rocks. It's not less impulse. Less momentum of falling rocks. No. More time to change the momentum of falling rocks. That sounds important. Less time to change momentum of falling rocks. Oh gosh, let's get this right. Nets used to catch falling boulders on the side of rocky hillside roadways are more effective than rigid fences because their breakage is reduced by more time to change momentum of falling rocks. So if you have falling rocks that hits a solid fence, there's a short time, meaning a high force to stop the boulders, meaning that's susceptible to breakage. Whereas if it's a net, it's got plenty of time for cushion to bring the rocks to a stop, which means a low force and a high time for the same impulse. So I think more time. Yeah. Standing still on a skateboard, you catch a ball tossed horizontally to you. The mass of the ball is 1/10 your mass. Compared with the speed of the caught ball, the speed that both of you and the caught ball require is, well, it's not the same because you're gonna be less than the original speed of the ball because you caught the ball and now the mass of the ball and you together are much higher than the ball was initially. The speed of both you and the caught ball require is, well, it's certainly not 10 or 100 times as much. It's going to be lower. So the only acceptable answer is 1/10 as much. Okay. This has got weird formatting here. When Jake tosses a ball while standing still on his skateboard, he and his skateboard recoil. If he goes through the motions of tossing the ball but doesn't toss it, his net recoil ideally will be the same as if he threw the ball. That's not true because the ball has to go somewhere and carry momentum away for the recoil to happen. Almost as much as if you threw the ball. Probably not even close. Very small. 0. It's going to be 0. Sometimes you might get a very small recoil, but there's probably friction with the ground, not the actual momentum change. So 0, because it says ideally here. When you say momentum is conserved, you mean that when an impulse acts on an object, its momentum will change. That's not really conservation of momentum being conserved. That's about what causes changes in momentum. Momentum can be stored. I'm not sure what that means. When external impulses don't occur, a system's momentum remains the same before and after an interaction. I think that's true. That's what conserved means. If there's no external impulse, then momentum remains the same. It sounds like conservation of momentum. When two objects collide, the mass and velocity of each object will not change. That doesn't sound right, so I'm going to go with this one. Okay. In the absence of external forces, momentum is conserved in elastic collision. That's true. Inelastic collision. That's true. In either an elastic or an inelastic collision. That's true. neither an elastic or inelastic collision. That's not true. It's always conserved, whether it's an elastic or inelastic collision. So I think this third one, yeah. A big fish coasts up to and swallows a small fish at rest. Right after lunch, the speed of the big fish is less than before. Because the big fish, he coasted up, ate a small fish, and then after, he's going to slow down a little bit because he picked up some mass. So it'll be less than before. Okay. A big fish swims up on and swallows a small fish at rest. Right after lunch, the momentum of the big fish is the same as before, maybe less than before. I don't think so, because it's conserved. More than before? I don't think so, because it's conserved. 0. No, because it was moving before. It's got to be the same as before, because we're talking about momentum. So if the initial momentum is the mass of the fish times its speed, the small fish is at rest. So it's going to pick up some mass. Speed is going to go down, but overall the momentum will be the same as before. There we go. A piece of clay moving with 1 unit of momentum strikes and sticks to a heavy bowling ball initially at rest. Okay. After the clay sticks, both the clay and the ball ideally move with a combined momentum of... Okay, let's read that one more time. Piece of clay with 1 unit of momentum strikes and sticks to a heavy bowling ball. So we're assuming the clay is much smaller than the heavy bowling ball. So after the clay sticks, both the clay and the ball ideally move with a combined momentum of... It's going to be 1 unit because the initial bowling ball is at rest and we have no external forces or impulses. So the initial momentum of 1 unit of clay, even though there's a difference in size, it'll be 1 unit after. Okay, there we go. A pair of spiral galaxies collide and merge to form one larger elliptical galaxy. Astronomers assume that the momentum of the new elliptical galaxy is equal to the sum of the momenta of the 2 spiral galaxies. That looks good. Equal to the difference of the momenta. I don't think so, because conservation of momentum is about summing up momentums. So the total momentum before will be equal to the total momentum after. So the total momentum before is the added up momentums of the 2 galaxies. And the momentum after is the momentum of the elliptical galaxy. Those 2 momentums should be the same. So we're going to assume that the elliptical galaxy has the same momentum as the sum of the 2 spiral galaxies before. So I think it's A, this first one. The same as the momentum of the more massive spiral galaxy. Well, that's not true. It's got to be both galaxies together. 0, that's not right. Equal to the difference in momentum of the 2 spiral galaxies. Well, it's not the difference. So this first one is the right answer. Okay. And that's it. That's our lecture about momentum. And I'll see you guys next time for energy. If you have any questions, let me know. You can email me or send me a message on Canvas.